In the following movie, we'll perform an axisymmetric, transient, bidirectional, coupled, thermal, flow, structural, flight cycle analysis of the compressor section of a gas turbine engine. We'll begin by creating the models in the Simcenter multiphysics coupled environment with the 2D solid plane in the ZX plane. We'll take the defaults for creating a solution. Then we'll begin by creating a mesh on the geometry. Here we have a number of different types of supported elements for creating our mesh, both triangular and quadrilateral. We'll use the axisymmetric parabolic triangles for meshing the hub and the case, and just those sections of the case that are not plane stress. Here you can see we're going to exclude one of the holes. We'll mesh that later with a different element type, which will be a plane stress parabolic triangle. First we'll mesh all of the blades into the same collector because they're made of the same material. However, for the hole that's made of a different material, we'll mesh that into its own collector. First, what you'll note is that the mesh is not congruent across some of the boundaries. So we'll make it congruent by stitching those edges to their adjacent edges within the tolerances that we can set. Update the mesh, and here now you can see we have a congruent mesh. Next we'll assign some physical properties. We'll begin on the hub and the case, which is made of the same material. We'll assign that 718. Now the hole also has the same Inconel material, 718. However, since it's plane stress, we need to assign a thickness. We're not going to do it in the physical property. What we'll do instead is assign it using mesh-associated data. Here we have a hole thickness source, so it understands the geometry as a whole, and we need to then only put in the number of instances, and it will automatically assign the thickness to the hole. Here we can plot those thickness contours. For the other plane stress regions, we'll use a different technique, which will be first to assign the material. We'll select waspaloy, and then we'll select a thickness for a single instance. Here we'll select 2 millimeters for all of the blades. If we wanted to assign separate thicknesses, we could do so. For this demonstration, we'll assign a single thickness and then assign the instances as part of the mesh-associated data. So here we have 35 blades for our first set of blades, 36 for our second, and we'll continue on the line assigning different numbers of instances as well for the remaining blades. Then we can plot the thickness contours for those plane stress regions as well. Next, we'll create a condition sequence. Now we already have defined a condition sequence. We'll go ahead and import that. The condition sequence consists of 3 tabs, one for condition sequence, second for conditions, and third for parameters. In the condition sequence tab, you have the time and the conditions that are prevalent at that specific time. On the conditions tab, we can set the conditions for each of the parameters. So here for condition 1, you can see the various parameters and their values. Condition 2 and condition 3. Here you can see the parameters, and what we'll do is we'll add an additional parameter. Here we'd like to put in a custom heat transfer coefficient that's going to change with the flight cycle. We'll define it as a convection coefficient and supply the units that we'd like to input the conditions with. So here for condition 1, we'll assign a heat transfer coefficient, condition 2, and condition 3. Now, since we have a condition sequence, we can use that to create a new solution with all of the time steps defined from the condition sequence. So here we'll go ahead and rename this to thermomech, and we'll also see all of the time steps that came in from our condition sequence. Next, we'll begin by assigning some loads. We have a thermal stream load that will apply to a section of our axisymmetric model. Here we can define that location using the path selection, selecting the beginning and the ending edge, and the software will find the path between those 2 selections. We'll then select a fluid material, a mass flow parameter, which we have a value of W26 in the condition sequence defined, which will vary through the flight cycle. Same thing with our inlet temperature. And we can add formulas. Here we'll add 25 degrees delta K. Select the units that we want for inlet temperature as well. Assign a pressure and a heat transfer coefficient. And make sure that we have the correct units assigned. All right, now to accelerate the demonstration, I have a model where I have already assigned many or almost all of the thermal loads continuing along. And I've left a few more to assign, which we'll do now, that will show some of the additional capabilities of the multiphysics environment. So here we'll assign another thermal stream load, and we'll call this thermal stream %% ID, which will look to the boundary condition ID for the name. So the %% ID will be 3 in this case. Here again we'll assign the fluid material, put in a mass flow parameter that will be the outlet mass flow of the upstream exit. So for stream 2, which is going to be just upstream of our stream 3, which we'll define the path in just a moment. Same thing for our inlet temperature, that will be the outlet temperature of stream 2. We'll put in a pressure. And here for our heat transfer coefficient, we'll assign that condition parameter that we defined earlier in our condition sequence. So here we'll define our path, selecting the beginning and ending edges. All right, next we'll create another thermal stream. This will be thermal stream 7. We'll do the same %% ID and give it the correct number, 7. Then for our mass flow parameter, what we'll do is we'll use one of the custom functions, and you can also add additional functions as well. This one, the one we'll select, will return a mass flow rate that will be the result of the mixing of two streams. So here's stream 4 and there's stream 6. We'll mix the mass flow in order to find the mass flow for our stream 7. We'll do the same thing for our inlet temperature. Mix is for mass flow, mix is for temperature. We'll put in a pressure and a heat transfer coefficient. And we can put those values in whatever units we're comfortable with. All right, next we'll define a thermal void. This is the region here in between the hubs. This is not defined with a path selection, but a simple edge selection. And we could try to accelerate that if we had some tangent continuous edges. We can try that. I'm not sure that we do. And it looks like these are not tangent continuous. So then we'll define our pressure and heat transfer coefficient. And for the heat transfer coefficient, what we're going to do is make the heat transfer coefficient a function of the radial location within the void. And the way we'll do that is we'll put in a scale factor of 1,000 times x, which is our radial location. But now the units of this are going to be meters, because x is defined in meters, so we need to divide that by 1 meter in order to make the heat transfer coefficient unitless, which will then allow us to select a unit from the unit dialog. All right, then we'll put in a heat load if we'd like, and a fluid material. And that defines the void. But we weren't careful in the numbering of that void. We'd really like it to be number 4. So let's go ahead and do that. So there you can see it comes up as V4 because it had the % ID in the name. All right, then we'll go ahead and organize the streams and the voids into their respective folders to organize our loads. And here we can plot the contours of the heat transfer coefficient that we just applied, and you can see here that it varies with the radial location, just as we had specified. All right, next we'll apply some constraints in just a moment, but first we'll put in another load. This one will be a structural load. We'll apply a rotational load about a subset of the model, which is just the rotating parts of the engine. Here we don't want the case. I'll shift to deselect that, and then we'll put in our velocity from our condition sequence for NH, the high rotor speed. Next we'll put in some constraints. We'll fix certain locations of the model. put in fixed constraints. Then we'll also put in a user-defined constraint, which will constrain the model in the radius only, in the radial direction. And we don't want the vertex. We'll go ahead and shift to deselect, or say deselect all, and select the edge instead of the vertex. Now we're ready to solve. And this is going to be a real-time solve. It takes a little less than 2 minutes to complete. But while it's solving, we can watch the progress of the solution. Now it's kicking off not just a thermal or just a structural, but a coupled bidirectional thermal flow structural solution. And that's managed by the Simcenter multiphysics interface. So here we can track the results of the solution for a number of parameters. We'll select the solid temperature, and this will show us the min, max, and average solid temperature for the entire model as the solution is progressing. And you can see how the time step is not constant. It is able to automatically adjust based on the delta t that's occurring or being recorded as part of the solution. So when the model is being more highly transient, there are more frequent time steps at a smaller interval, and then as the model becomes less transient, it's able to solve more efficiently by increasing the time step. All right, and we're up to our last time step, and the solution is just about complete. And just a little bit under 2 minutes. Now we'll begin by taking a look at our structural results. You can see we have both structural and thermal results. Here you can see we have structural results at the various time steps that we've defined earlier in our condition sequence. Next, we'll animate across all of those time steps. You can see how the model grows and shrinks based on the condition sequence parameters at the various time steps. You can see how in most locations the tip clearance appears to be increasing, except for one here. Looks like we may have an interference. And we'll go ahead and resolve that by putting in edge-edge contact. We'll do that in just a moment, but first we'll take a look at our thermal results. And here you can see how the temperatures are varying throughout the flight cycle. Now, just to double check on those tip clearances, what we can do is create a result probe, which we'll title clearance for, we'll call it blade number 1. And I have a formula here which uses reference points, which we've defined in the model. We'll take a look at those in just a moment, in order to calculate the distance between the blade tip and the case. Here we can go ahead and plot those clearances now as a function of time. And you can see here how the blade tip clearance does grow and shrinks, but always stays positive for this blade. Here you can see those points. There's our ref point blade 1 and ref point case 1, which we had put into our probe equation. So here we have blade 4, ref point blade 4, ref point case 4. Here we'll go ahead and put in the equation with blade and case point 4. We'll give it a new name, clearance 4, and we'll go ahead and we can plot that one as well. And you can see here how this one goes negative, showing the interference. And it looks like it goes negative right around 200 seconds. So to make the model more accurate, let's put in some edge-edge contact. But before we do that, we'll clone the solution to make another copy of it so we can keep the results from our original run. And we'll call this new solution thermal mech contact. Then we'll put in our edge-edge contact. Now this edge-edge contact is not only a structural contact, but also can be a thermal connection to the model as well. So here for our source region and target region, I've already defined the edges on the case and the blade tip. We'll go ahead and put in coefficients for static friction and a search distance. Then we'll activate the thermal coupling. This allows us to create a thermal mechanical contact which will change the heat transfer coefficient based on whether or not contact is occurring. So here we can see if it's not occurring, we'll make it one value, and if it is, we'll make it a different one. So now we'll go ahead and solve the updated solution. That includes the contact. This one I'm going to pause the video. You'll see how the time will jump in the solution monitor. This one, since it incorporates contact, takes closer to 3 minutes. All right, now let's take a look at our updated results for our contact run. And here we'll begin by plotting our clearances. Here you can see for case and blade 4, we can see right around time step 200 seconds, we're pretty close to 0. And it doesn't go negative because of the contact. Let's go ahead and take a look at the structural results. And we'll focus on the location that we assigned the contact and animate across our time steps. And you can see the contact, how that affects the structure and the temperature results of the model. So there you can see the difference in the structural result. Next, we'll take a look at our temperature results. And to see this a little bit better, what we'll do is look at it side by side with our run where we did not incorporate the thermal mechanical contact. This is our previous run. We'll synchronize the views so that when I zoom in on one, it zooms in on the same location on the other. And then we'll go ahead and animate the temperature results across the various time steps. And what you can see here on the left is where we have the contact incorporated. We're not looking at any deflected shapes. And on the right, we do not have the thermal mechanical contact, and you can see the much greater temperature difference between the tip of the blade and the case. So here you can see the contact occurred or began to occur at about 200 seconds. So everything greater than 200 seconds, the temperatures are much closer between the blade tip and the case. And that concludes the demonstration.